Your lecturer is Francis Su. Dr. Su is a professor of mathematics at Harvey Mudd College. His work has been featured in the New York Times, and Wired magazine called him the mathematician who will make you fall in love with numbers.
I'm really excited to take you on a tour of linear algebra, a foundational subject in mathematics that is both powerful and beautiful, with classical roots and modern applications. In this first lecture, I'll try to give you a sense of what linear algebra is, why it is important, and how it can help us solve some interesting problems. And in later lectures, we'll dig into some of the finer details of the cool ideas you'll encounter, but think of this lecture as an introduction to some of the big themes of linear algebra. Now, you may hear the word linear and think linear algebra has to do with the study of lines. Or you may hear the word algebra and think that linear algebra is related to high school algebra, manipulating expressions. Or maybe you've heard that linear algebra has to do with the study of matrices. Now, all these things have their place in the study of linear algebra, but they do not give the big picture, which exhibits a really rich interplay between algebra and geometry, between computation and visualization, between the concrete and the abstract, and between utility and beauty. There's even a fun word used in linear algebra that reflects our desire for beauty: transformation. This is really just another word for function, which you might recall is a rule for taking an input, like a number or a set of numbers, and assigning an output, another number or a set of numbers. And in linear algebra, we like to call functions transformations because we think of them as changing one picture into another. We also call the second picture the image of the first. For instance, right now, you see a view of me holding up my hands. And if I change position, you'll get another view of me. And even though I haven't changed, your view of me has changed. My arms now appear to be in a different angle than they were before. It has undergone a transformation. So the mathematical idea of a transformation is very similar. There's a function that changes the view by assigning every point or object in the old picture to an image in the new picture where it is moved. You can see this kind of transformation might be important in computer graphics if I want to change perspective. But there are lots of other kinds of transformations. I like to snack on nuts and chocolate, but I also care about eating healthy. Not a great combination, I know. Suppose I do some measurements on a collection of X chocolates and Y nuts and find that they have m grams of carbohydrates and n grams of fat. That is a transformation of two numbers, X and Y, into its image, two numbers, m and n. So now we're ready to define the term linear algebra. Linear algebra is the study of certain kinds of spaces called vector spaces, and the study of special kinds of transformations of vector spaces, called linear transformations. And our goal today is to give you a sense of what a linear transformation is and how it arises in many contexts where you wouldn't expect. First, let me give you an idea of what the word linear means. When I was a kid, I would look up at the night sky, and I lived in a rural part of Texas where you could actually see the stars. And I enjoyed hunting for planets. And you could tell the difference between a planet and a star because, unlike stars, a planet does not twinkle with the motion of the wind. And because the Earth and the planets move in relation with one another, the planets move against the backdrop of stars, so that if you look up at the night sky on consecutive nights, a planet would appear to have moved ever so slightly. And this is a perfect backdrop for understanding linearity. We imagine our view of the night sky as being represented on a two-dimensional plane. Suppose that you find the planet Saturn and mark its position on night 0 and night 1. On night 2, where should you look? Now, you may not know anything about the motions of planets, but that's actually a good thing because it'll illustrate my point, which is, absent of any other information, there is really only one reasonable guess as to where Saturn will be on night 2. Yes, that's right. You naturally assume that Saturn's motion from night 0 to night 1 will continue in the same direction and at the same speed as it moves on subsequent nights. And we call this motion linear. So on night 3, you would expect to find Saturn here. One feature of this motion is that no matter what night you start observing, the planet will traverse the same distance along that line from night to night. With linear motion, the distance and direction traveled depends only on the time elapsed, not on the position you start. Now that we've seen geometrically what's happening, let's try to understand what's going on algebraically. Imagine our view has coordinates, and suppose we find Saturn at point 0, 0 on night 0, and at point PQ on night 1. Then on night 2, we expect to find Saturn near PQ plus PQ, which is the point 2P, 2Q. And more generally, we can see that at time t, Saturn should be at the point 0, 0 plus t times PQ. If you think of t as time, then as time varies, this expression traces out a line with constant speed. This is a function that takes a time t to its image, which is a position in the sky. Of course, planets do not move in straight lines either in the sky or in real life. However, if the planet's motion is relatively smooth, we can expect that for small timescales that the formula would actually be quite good. That's because when a path isn't linear, it is often approximately linear. And this idea is actually at the heart of calculus, a subject you may have seen before. When you encounter a crazy function, calculus suggests that you try to approximate it by something you understand better. The graph of a function that is not linear can, if it's simple enough, be approximated by a line. And that's what's going on in this example. Because we only had 2 data points, we assume that Saturn moves linearly as a function of one variable, which is time. But this idea of linearity also makes sense for functions of several variables. For example, you might have a function t that takes a position in the plane to another position in the plane. Suppose I wanted to take a square grid like this in the left picture and convert it to a picture on the right, which looks like the same square grid but viewed from a different angle and distance. If you were doing computer graphics, you might want to have the ability to change perspective like this. The function t that performs this conversion moves points in the plane around, and the diagram suggests how the points get transformed and how lines and arrows on the diagram get transformed as well. For right now, I won't bother you with actual formulas, but this change of perspective is a linear transformation because it has 2 good properties that I want to show you. Look at the arrow in view 1 indicated by the letter V, which is based at the point 0, 0. The arrow twice its size and pointing in the same direction is labeled 2V. The transformation t has the nice property that the image of these 2 arrows are related in the same way in view 2, twice the size pointing in the same direction. You can think of the arrow V as a small change in input. So this property shows that if I double the input vector, arrow V changing to arrow 2V, the output should double as well. In other words, double its magnitude but retain its direction. The arrow t of V changes to the arrow twice t of V. So here's the first linearity property. For any real number k, t of k times v is k times t of v. Said another way, it doesn't matter whether you scale first, then apply t, or apply t first, then scale. There's a second good property of this transformation. If I'm anywhere else besides the origin and I modify my input by v, then the output changes by t of v no matter where I was to begin with. Compare the arrows marked v, starting at w, with the arrow at the origin marked v. They represent the same change in input. Under the transformation, the pink arrow gets transformed to t of v at the origin, and the blue arrow gets transformed to t of v based at t w, but the 2 arrows marked t of v are the same and represent the same change in output. So we see this transformation as the same property as the Saturn example did. Equal changes in input, in that case it was time, lead to equal changes in output. And this highlights the second linearity property. T of W plus V equals T of W plus T of V for any points V and W. Said another way, the transformed sum is the sum of the transformed points. Or another way, it does not matter whether you add first and apply T, or apply T first, then add. So the change of perspective in computer graphics is also a linear transformation. Linear transformations arise in many ways. Do you remember that when I snack, I like to calculate how many grams of carbs and fat I'm eating? Well, suppose X is the number of chocolates I have and Y is the number of nuts. Then if a single chocolate has A grams of carbs and a single nut has B grams of carbs, then the total carbs in my snack is AX plus BY grams. Similarly, if C and D record the number of grams of fat in a chocolate and a nut, then I'd have CX plus DY grams of fat. So if A is the transformation that takes the number of chocolates and nuts to the numbers of grams of carbs and fat, then it is represented by A of XY equals AX plus BY, comma, CX plus DY. You can check that if you vary X by 1 unit, the output changes by A, comma, C grams, no matter what X and Y are. Similarly, if you vary Y by 1 unit, you get similar behavior. So this transformation is linear too. What you see here is an example of a system of equations. AX plus BY equals carb grams, and CX plus DY equals fat grams. Systems of equations, often with many more variables and equations, arise in so many applications that one of the most important questions you can ask mathematically is how to find solutions to such equations. And linear algebra will help us do that. One of the ways we do that is to represent coefficients of a system in a matrix, which is an array of numbers. Matrices, which is the plural of matrix, matrices have their own algebra, operations that you can do with them, and we'll explore those. And since it turns out that every linear transformation can be associated to a matrix, learning how matrices behave is a big part of doing linear algebra. At the same time, systems of equations can be understood geometrically too. Each linear equation has a solution set that is a linear object, like a line or a plane or a hyperplane. So to solve a system of equations simultaneously can be understood as intersecting a bunch of hyperplanes and asking what, if anything, is in the intersection. We have seen many ways in which linear transformations arise, and it seems appropriate now to highlight this as the first of several important themes in this course, and reasons that you'll want to learn linear algebra. Theme 1. Linearity is a fundamental idea in mathematics and in the world, and you will encounter it everywhere. We have seen, for instance, that linear transformations describe the geometry of a change of perspective. And if we know how to represent them by a matrix, we can compute them fairly easily, as we shall see. If you were producing computer graphics and you wanted to rotate an object, or scale an object bigger, or flatten a 3D object to a 2D object, these are all linear transformations. We have seen nutrition depends on ingredients in a linear fashion, but there are many other linear relationships in our lives that may not be obvious at first glance. For instance, suppose you wanted to measure the importance of a web page. One way to do that is to imagine a person surfing the web. She starts at one web page, she picks a link on that page at random, and she hops to that page. She repeats that process with a new web page. Then after many hops, you might expect that she is more likely to be at a popular page than at a less popular one, because a popular page will have many paths to get there. This gives us a way of ranking pages. So imagine a very simple web with just 2 pages, page 1 and page 2. Suppose there are 4 links from page 1 to itself, which could happen if the page linked to another part of the same page. And suppose there is a single link from page 1 to page 2. And let's say page 2 has 3 self-links and 2 links to page 1. If the probability of being at page 1 is x, and the probability of being at page 2 is y, then after one hop, what are the probabilities of being at those pages? Well, you can get to page 1 either from page 1 or page 2. So the probability of being at page 1 after one hop is the probability of going from page 1 to page 1, which is 4/5, times the probability of starting at page 1, call that x, plus the probability of starting at page 2 and going to page 1, which is 2/5, times the probability of starting at page 2, call that y. This is just 4/5 x plus 2/5 y. Now the probability of being at page 2 after one hop can be computed in a very similar way, and we get, by inspecting the link diagram, 1/5 x plus 3/5 y. So the two probabilities of ending at page 1 and page 2 are given by linear equations, much like the ones we had for nutrition of chocolates and nuts, and can be represented by the linear transformation t of x comma y equals 4/5 x plus 2/5 y comma 1/5 x plus 3/5 y. To get the probability vector of being at page 1 and 2 at time n plus 1, which we'll call x sub n plus 1 comma y sub n plus 1, we can just apply t to the probability vector at time n, which is represented by x sub n comma y sub n. So if we had a way of computing repeated linear transformations quickly, we could then perform this linear transformation, t, 100 times to get the probability of being at pages 1 and 2 after 100 steps. Larger probabilities then correspond to popular pages, and we would have our own version of PageRank. So here's a second theme that we've already seen in the night sky example. Theme number 2. To understand nonlinear things, we approximate them by linear things. Things in the world that are not linear are often approximately linear. In multivariable calculus, when we encounter graphs of nonlinear functions, we approximate them locally by tangent planes if they're what's called differentiable. In statistics, when we encounter a cloud of data points, we often assume linear relationships and use regression to try to fit the best line or hyperplane. Or maybe we try to reduce the dimensions of the data to something manageable by finding special directions in which there is a lot of variation. Returning to my nutrition example, suppose that I were looking at my snack of chocolates and nuts, not as a consumer, but as a producer. So I'm wondering about the cost and time of producing chocolates and nuts. Cost and time are not linear functions of quantity. You can see this because if they were linear, then the cost to produce one more nut would be the same no matter how many nuts you had produced already. But usually there are efficiencies that you can gain from mass production, the so-called economies of scale. So the cost to produce an additional nut or chocolate is actually cheaper after you've produced a lot of them. And the additional time it takes is much smaller too. So whatever transformation t that takes quantities to cost and time has to be nonlinear. But the nice thing is that it, like many things in this world, is locally linear. That means that if I know how much an additional nut adds to time and cost, and how much an additional chocolate adds to time and cost, then that is enough to approximate how much additional time and cost it takes to produce any small numbers of chocolates and nuts. For those of you who've taken multivariable calculus, this is why the derivative of a multivariable function is given as a matrix, because it's a linear transformation that provides the best linear approximation to that function. Theme number 3. Linear algebra reveals hidden structures that are beautiful and useful. We have seen that linear transformations arise in many contexts, so that, for instance, if you know quantities x, y of snacks, you can figure out fats and carbs. But what if you know fats and carbs and you want to solve for quantities x and y? This is the problem of solving a system of linear equations. It might be easy with functions of two variables using substitution, but if you had a large number of variables, this strategy won't work. You'll have to be more systematic. And linear algebra can be useful here because much of what linear algebra does is reveal hidden structure, and then it uses those structures to give us the insight into what is really going on. Such insights often allow us to solve problems a simpler way. For instance, I may not be able to see if a system of equations has a solution just from inspection. But if I see the system of equations as arising from a linear transformation of some variables, I may be able to put those equations in a simpler form. And matrix algebra, which underlies the algebra of linear transformations, seems strange at first and has a lot of hidden structure that turns out to be really useful. For instance, let's return to the simple two-page web. Recall that the link structure had this picture. And this linear transformation T converted the nth step probabilities of being at pages 1 and 2 to the n plus 1th step probabilities of being at pages 1 and 2. Here, T of xy equaled 4/5 x plus 2/5 y, comma 1/5 x plus 3/5 y. So if you start at page 1, to find the page probabilities after 100 hops, you just apply the linear transformation T 100 times to the initial starting configuration, 1, 0. Can we do this quickly? This may not be a big deal for a simple transformation, but it can make a big difference with large numbers of components and variables. Now before we do it, take a moment to guess the answer. If you start at page 1, what are the page probabilities after 100 steps? Do you think you are more likely to be in page 1 or page 2? The calculation can be done very efficiently because the transformation T has special vectors, the so-called eigenvectors, for which applying T is very easy. Look at this vector, 2, 1. Notice that when you apply T to 2, 1, you just get back 2, 1. In other words, T doesn't do anything to 2, 1. So if you apply T to 2, 1 99 more times, it's still unchanged. Now look at this vector, 1, minus 1. If we compute T of 1, minus 1, we get 2/5, minus 2/5. And the key insight here is that 2/5, minus 2/5 is actually a multiple of 1, minus 1. So T of 1, minus 1 is just 2/5 times 1, minus 1. And if you multiply by A 99 more times, it'll just be 2/5 to the 100th power times 1, minus 1. If I start on page 1, the beginning vector of page probabilities is 1, 0, since there's no chance of being in page 2. This vector is not a special vector, and the function T does not act on 1, 0 in a very nice way. But if we notice that 1, 0 can be written as a combination of the special eigenvectors, in fact, it is 1/3 of both eigenvectors summed. So then something amazing happens. The first and second linearity properties ensure that we can apply T first to 2, 1 and to 1, minus 1 before we scale or sum them. But those actions are very easy on those special vectors. T does nothing to 2, 1, and it multiplies 1, minus 1 by a factor. Each additional time we apply T, it just multiplies the second eigenvector by that same factor. This means that T to the 100th times 1, 0 is just, by the linearity properties, the sum 1/3 times 2, 1 plus 1/3 times 2/5 to the 100th times 1, minus 1. And this is easy to compute. Notice how small the second term is. The first term is 2/3, 1/3, and it dominates. So we see that in the long run, after many hops, the likelihood of being in pages 1 and 2 is 2/3 and 1/3. So, did you guess correctly? This calculation shows that page 1 is more popular than page 2. And search engines like Google use mathematics like this to rank how important pages are. Pretty neat, right? Theme number 4, linear algebra's power often comes from the interplay between geometry and algebra. With every new concept in this course, we'll learn how to think about it algebraically and geometrically. Algebraically means in terms of algebraic expressions, geometrically in terms of things we can visualize. For instance, the set of solutions to a linear equation in 3 variables, like x plus 2y plus 3z equals 10, represents some plane in 3-dimensional space. So if I know this, then I know if I have 2 such linear equations involving x, y, and z, the set of solutions that satisfies both equations will be the intersection of 2 planes, which in most cases is just a line. If the 2 planes happen to be the same plane, then the set of solutions may also be a whole plane. But if the 2 planes happen to be parallel and disjoint from each other, then the pair of equations may have no simultaneous solution. Notice this insight came very easily from the geometric view of these algebraic equations, but may not have been obvious just by looking at the equations. This kind of interplay between algebra and geometry is indeed very powerful. So, in this lecture, we've seen what a linear transformation is. We've gotten a glimpse of how linear algebra can help us understand many things we deal with on a daily basis. We've seen several important themes in linear algebra, that linearity arises everywhere, that nonlinear things are often approximated by linear things, that linear algebra can reveal hidden structures that we can delight in and use, and that the interplay between geometry and algebra is very powerful in linear algebra. And as you watch the coming lectures, you'll want to supplement them by working problems from a book on linear algebra. Almost any standard text would do, but I'll make some suggestions in the guidebook that accompanies this series. Working problems is an important way to make sure you understand the concepts you encounter. Okay, next time we'll talk about the basic objects of linear algebra, vectors, and we'll show you many different ways to think about them.